Howdy, everybody. I know we've been working with work energy for a couple of class sections, but I'd just like to kind of summarize where we've come and get us to the next place. We've seen that work is force times distance. And specifically, when work is conducted at an angle, it's really the cosine of that angle times the force times distance. Of course, if the angle is zero, meaning the force and the displacement are parallel to each other, the angle between them is zero, then the cosine of zero is 1, and this just simplifies to that. That when work is done in lifting an object to a new height, that the force that we exerted was the weight of the object, and the height is the distance. And so work equals force times distance becomes mgh. And this results in a change in potential energy. So in this case, work is achieving a change in potential energy. We've also discussed how objects in motion have a different kind of energy called kinetic energy. And work can change that as well. When a pitcher winds up and throws a baseball, they exert a force over a distance on the ball, and that ball has a resulting change in kinetic energy. Now, in both cases, I've just called the change the final, and the change the final kinetic energy, in this case, potential in this case. Of course, it's really the final minus the initial, but I'm assuming that there was no potential energy to start with and no kinetic energy to start with, just to simplify the equations. The real thing that I would like to get across today is this idea that total energy is often conserved. If there are no forces acting like friction that steal energy and turn it into heat, or that's typically where lost energy goes, into heat, in the absence of such of a non-conservative force, total energy is the same before, after, during, at all times. So the only exception to that really, other than work done by a non-conservative force like friction, is work. If you do work, you change energy. So let's just say that you have a 10 kilogram object. It weighs 98 newtons, of course, because mg is 98. And you lift it from the ground to some height, let's say 3 meters. What's the potential energy after lifting it? Well, it technically is the same as the work that you just did. Force times distance, which is going to be mg times h. So the potential energy at the top, mgh, so we see that you have 294 joules of potential energy at the top. The total energy, if it's not moving, is 294 joules, because of course the kinetic energy is 0. Why is the KE 0? Because it's not moving, and KE equals 1/2 mv squared, and if v is 0, KE is 0. So the total energy is 294 plus 0, which is 294. Here's the point. As it falls, it's losing height. And because it's losing height, it's losing potential energy. It will lose potential energy as it falls. Where does that potential energy go? It turns out if no forces are stealing energy and turning it into heat, that energy turns into kinetic energy. For every joule of potential lost, we gain a joule of kinetic. So that the sum of the two, PE plus KE, will always equal 294. even a third of the way to the ground. So let's just pick an arbitrary place and let's find the speed there. Let's just say at a height of 1 meter. What would be the speed? How do we do that problem? Well, we know that the total energy is PE plus KE, and that equals 294. It's going to equal 294 at all places along the way. So the KE, why do we want to find the KE? Well, we want to find the speed. And we know that the KE depends on the speed. So the KE at the at 1 meter is going to equal 294 minus the PE at 1 meter. So let's go ahead and find the potential energy at 1 meter. The potential energy at 1 meter is mgh, which is, of course, mgh, which in this case is going to be 98. Because, of course, 10 times 9.8 is 98, times 1 is 98. So 294 minus 98 should be how much energy has turned into kinetic energy at the 1 meter mark. And that equals 196. So the KE at 1 meter equals 196 joules. Now, how can we find speed from that? Well, we know kinetic energy equals 1/2 mv squared. So if we just take this relationship and solve it for v, we get the answer we're looking for. To solve KE equals 1/2 mv squared for v, we multiply by 2 and then divide by m and then take the square root. In other words, KE equals 1/2 mv squared. Multiplying by 2, we get rid of the 1/2. Dividing by m, we get rid of the m. And taking the square root, we get v. So v can be found from knowing the kinetic energy and mass by multiplying the KE by 2, dividing by m, and taking the square root. We know that KE is 196. So 2 times 196 divided by the mass, square rooted. This all becomes 39.2, and the square root of 39.2 is 6.26. Rounding that off to 2 sig figs for fun, we're going to make that 6.3 meters per second. So what have we done? We've looked at this idea that energy, the total energy, KE plus PE, is always the same number everywhere along the path down to the ground. And we knew that the total was 294 at the beginning, so we said at any place, for example at 1 meter, what will the kinetic energy there be? Because we want to find speed. It's the KE plus PE equals the total, so KE equals the total minus PE. We found that PE just using our MGH equation, subtracted 98, got 196, and solving the kinetic energy equation for V gives us the square root of 2KE over m. We plugged in our values and got our final answer. We could have used kinematics. We could have just dropped an object and found the displacement, found the speed 2 meters lower, right? We called the top 3. We wanted to know about 1. The difference between 3 and 1 is 2. We could have just dropped the object 2 meters and used kinematics. But we will see later on that there are many occasions where energy is a more powerful method for solving problems. And I think today we'll see that.